Yeah, first of all, thank you, Vincent, for the introduction and the invitation here. Thank you all for coming to this Zoom presentation. It's a pleasure and an honor to share results from the last, I don't know, 5 beam times I've been to. So I will try to show experiments I did at the University of Cambridge with the help of a lot of collaborators. So all the experiments I will show were made by many people. Most of all, I would like to thank people from Helmholtz Center Berlin, NREL, Samstrangs, and also from the University of Potsdam right now. So in the next half hour, I would like to tell you something about the radiation tolerance of a variety of different perovskite-based tandems. I would like to start and try to understand radiation damage in those tandems, but then also I'll have an outlook about other open challenges, and there I will try to review results from literature. And I'm very looking forward to maybe have a discussion with all of you here. So I've seen many people working on radiation hardness and space applications, so I'm looking forward to that. So let's jump right in, and I would like to start with a question. So why do we need perovskite-based multijunctions in space? And the answer is quite simple, and I think all of you know this here. So perovskite are direct semiconductors, and they have a very strong absorption coefficient, meaning that less than 1 micrometer of material is enough to make an efficient solar cell. So they're ultra thin, lightweight, and flexible, which is of course great for space if you think of a solar cell which you want to unfold or unroll once launched into space. And the picture I'm showing here on the left is actually an OPV, single junction, made by Joel Jean. And I'm showing this because I like the figure, and also because it's, I think, the thinnest solar cell ever made, using just 1 micrometer of substrate, right? Okay, so single junctions are great, but then our satellites are becoming more and more energy demanding. So we also need efficiency. And to do this, we need to go for tandems or even triple junctions. And on the next slide, I'm trying to summarize this basically. And now I'm showing here the AM0 efficiency as a function of the weight of the solar cell and the specific power in watts per gram. And I'm comparing a bunch of different technologies here. And I know the graph is messy and confusing, but I'll try to guide you through. So the first thing here is these are triple junction 3.5 based solar cells, which are the industry standard for any space application. So this is indium gallium phosphide, gallium arsenide on germanium. And this is a wafer-based technology, which is efficient, but relatively heavy, and also not the cheapest. So if you want this to be lighter, you can then do an epitaxial lift off, and you can make even more expensive 3.5 triple junctions. So then I'm plotting here the potential of perovskite single junction, a perovskite tandem, and a potential perovskite triple junction solar cell for 3 different substrate thicknesses. Okay, so I'm assuming 20 micrometer, 50 micrometer, or 100 micrometer substrates. And I think all these 3 are actually technology feasible. So if you assume, let's say, the 100 micrometer thick substrate, we would end up at a specific power exceeding today's industry standard. And this is the high specific power potential I'm very excited about, which could lead to future applications in space. Of course, I must say here, all these current records for perovskites are still on relatively small area, while for the 3.5s here, you can maintain the efficiency even on larger substrates. So there's still a way to go for us to upscale this technology. All right, so if you want to apply any perovskite in space, one super crucial parameter is, of course, their radiation tolerance. So we all know that there is extreme radiation out there. We know this from increased cancer risk. We also maybe know that microelectronics are particularly affected because of single event upsets. So in this case, high energy particle, for example, flies through a transistor, and then the induced charge actually switches the transistor from a 0 to a 1, and this can lead to a blue screen of a computer, for example. So it's quite easy to shield microelectronics. You just need some millimeter, centimeter of aluminum around. But for solar cells, it's a bit more tricky because you need high areas, but you also want to have a low weight, right? So any solar cells in space, which is not shielded enough, will suffer from radiation-induced damage, which accumulates and then degrades the performance over time. The mechanism behind is basically nuclear scattering or displacement damage, in which, for example, a proton hits an atom in the lattice and then displaces this atom to an interstitial site. It can also be electronic scattering, in which a high energy particle ionizes and by this breaks any bonds in the material. So both effects lead to radiation-induced defects, which lead to additional non-radiative recombination. So I'm now trying to give some examples for different materials known from literature, basically. And I'd like to start with just glass, which we all use as a substrate for our solar cells, right? So silicon oxide, in silicon oxide, you start to form these color centers when you break a silicon-oxygen bond. And this darkens your glass. And this, of course, affects any solar cell behind that glass. It also affects crystalline silicon, which we use in transistors and silicon solar cells. And here people already know that you start to create these silicon vacancies. You can see them by EPR and DLTS measurements. But then, and this is quite crucial, if you are at temperatures above 100 degrees, these silicon vacancies start to complex with dopants in the silicon or with impurities in the silicon, and you start to form these phosphorus divacancy complexes or carbon-oxygen vacancy complexes, and these are particularly harmful and degrade any solar cell. So then one example of the other extreme is mercury indium telluride. This actually is a disordered defect zinc blade phase in which every 6 position is actually a disordered vacancy. Because of that, this material is extremely radiation tolerant. However, it's also extremely difficult to make transistors or solar cells out of this device. You can, for example, not dope it, and you're left with Schottky junctions. Then one last example now from the organics. And here I'm just taking P3HT as an example. And upon irradiation, it's well known that you basically break a CH bond, and then the hydrogen moves around the backbone of the P3HT and is a defect there. But you can also anneal it to recover performance. All right. So enough examples. Let's switch over to perovskite. And here there have been a plenty of tests under high energy proton irradiation by a number of different groups. So I will not try to summarize them all here. I think most people now conclude that perovskite single junctions are relatively radiation hard. And I've also seen this. And as promised in my talk, I now want to focus on tandems. So I'll be showing results on perovskite CIGS, perovskite silicon, and perovskite tandems. And the key question here is, can we translate results from single junctions? What is the monolithic interconnection doing? So for example, you could imagine that damage in just one subcell, for example, the perovskite here, degrades the performance of the overall tandem. And then lastly, what is about the required high and low gap perovskite compositions? Are these less stable than the standard perovskites? So these are questions I would like to answer. before starting into that, let's take one more step back, and I'd like to speak about the high energy particles in space. So damage is mostly dominated by high energetic protons, and there it depends in which orbit you are. So this plot here basically shows the differential proton fluence as a function of the energy for different orbits. So you have, of course, maybe heard of Van Allen bands. So which we always try to stay out. So for example, the ISS is in a relatively near orbit around Earth, still well shielded, but then some Starlink orbits are more outside, and then around Jupiter you have even higher radiation belts. So the stopping of high energy protons is a function of their energy, and the stopping power, dE over dx, scales with 1 over e squared, meaning that lower energy proton will be stopped faster. And this allows you basically to block very low energy protons quite efficiently already by 100 micrometer thick foils or 1 millimeter glass. For tandems, this is now also quite important because a certain proton energy would only damage one subcell in a tandem or in a triple junction. And here I'm showing calculations for a 3,5 triple junction solar cells, which was tested extensively on the protons. And you can see quite nicely that, for example, 68 kilo electron volt protons are only stopped in the top subcell and would only damage this. However, in space, we have a spectrum of protons with different energies, and they also come in different angles. And this then leads to very homogeneous damage throughout the entire solar cell, right? So I've been trying to simulate this for a perovskite tandem, and I'm now showing results here. So what I'm plotting is the energy lost by the protons in the individual layers. So the red here is the high gap top cell, and the blue is the low gap perovskite subcell. And you can see quite nicely that the damage is rather homogeneous for a variety of different orbits. And in order to mimic this, you need a very high proton energy, something like 68 MeV, which is what I've been using. And I've been using this from a very high energy proton accelerator at the Helmholtz Center Berlin. So this is basically a tandetron cyclotron combination accelerating these protons, and usually it's used for eye tumor therapy. So the downside of using these high energy protons, while they give you a very homogeneous damage throughout any device, is that you also have a third effect. And the third effect is inelastic nuclear scattering, right? So the high energy protons actually will start to create a bunch of short-living isotopes. And these isotopes here are what I usually find after irradiation of a perovskite sample. And because of this, we usually wait about 2-3 weeks before we start any after characterization, just for safety reasons. Okay. So with that, I would like to jump in for our first tandem. And this is a perovskite silicon heterojunction tandem made by Marco Jost from Helmholtz Center Berlin. This is basically a standard silicon heterojunction with a spin-coated triple-cut iron perovskite on top. It was very well functioning. And so here on the left, you can see a standard JV curve, and here on the right, the external quantum efficiency. So I've been taking this tandem to one of my beam times, and I would now like to show you an in situ experiment I've done during the proton irradiation. Basically, what I'm doing is I'm shooting protons at the tandem, while at the same time the tandem is illuminated and connected to a source measure unit, and I'm tracking the JV characteristics over time and over proton irradiation. And the results are basically shown here on the left. And you can see quite nicely that once we switch on the protons, the performance of that perovskite silicon tandem degrades very fast, especially the efficiency and the short circuit current, while the VOC and fill factor stay relatively constant. So now this is a monolithic interconnection of the perovskite and the silicon. So we don't really know what is damaging here. Is it the perovskite? Is it the silicon? In order to find out, I now did the following. I used these LEDs here and I reduced the intensity of my infrared LED while keeping the blue LED at a very high level. So in this configuration, then the silicon subcell will limit the overall current because we are in a monolithic interconnection. Saying that in this configuration, I will be sensitive to damage in the silicon subcell. And you can also do it the other way around, right? So now I'm reducing the intensity of the blue LEDs, while the infrared LEDs are at a very high intensity. So in this configuration, the perovskite subcell will limit the overall current. And by that, we will be sensitive to any damage in the perovskite subcell. When you do that, you can see quite nicely that, of course, the tandem JSC is decreasing rapidly. And mostly this is because of the silicon subcell, right? But also we see some damage in the perovskite top subcell. All right. So as said, these devices are relatively radioactive after proton irradiation. So we wait a couple of weeks, but then basically characterize these devices again. And you can see quite nicely that they degrade to 1% of their initial efficiency. All right. So the reason behind this degradation basically is that the silicon subcell degrades rapidly. And here the dashed line is measured after proton irradiation. But we also see some damage in the perovskite subcell. Interestingly, this damage, or this EQE, was really affected by a lot of artifacts while measuring. I'm still not 100% understanding those. However, under the right measurement conditions, we could almost recover that perovskite quantum efficiency here. So we think that the perovskite was not damaged and only the silicon. So in order to find out, we then started to do absolute photoluminescence imaging, and we did that using a hyperspectral PL microscope in Cambridge. So we excite with a blue light laser, only exciting the perovskite, and record that PL. So the PL is, according to Würfel's generalized Planck law, a function of the quasi-Fermi level potential. So we have an equation relating the PL intensity to the quasi-Fermi level. And here I'm doing this with a linear fit at the high energy slope to extract the quasi-Fermi level splitting. And by doing that, we can create a quasi-Fermi level image. And as you can see here, there's a slight reduction in quasi-Fermi level splitting in the perovskite, but it's not much, right? It's about 2 milli-electron volts drop here, while the tandem undergoes a very strong decrease in VOC. So this damage is not because of the perovskite, but it must be because of the silicon. And we've irradiated silicon single junctions as well. And we see this massive drop in VOC here. And we also see a reduction in PL of the silicon and a reduction in the lifetime of the silicon substrate. So we think we understand the perovskite silicon tandem device, and it's not good to use it in space. So with that, I would like to go over to the next tandem. And this time, this is a perovskite CIGS tandem, also made by Marco Jost from Helmholtz Center Berlin. I hope he's in the audience here. So again, this is a spin-coated triple-cut iron perovskite formulation on top of CIGS. And because of the roughness here, we used a double layer of PTAA and nickel oxide. And now I'm doing basically the same. I characterized these tandems before irradiation and then went to beam time to do an in situ experiment, again shooting protons while also studying the performance while irradiation. And I'm also doing the same experiment as before. So I reduce the intensity, for example, of the blue LEDs while maintaining the intensity of the infrared LEDs to be perovskite sensitive and the other way around to be CIGS sensitive. And the results are now shown here on the left. So I don't see any degradation in efficiency, JSC, fill factor of VOC, and then of course also in the perovskite top cell limiting or the CIGS bottom cell limiting, we don't see any change over proton irradiation. So this looks promising. We don't need perovskite silicon tandems. We can just use a perovskite CIGS. After irradiation, so after the activity dropped to a safe level, I again measured all tandems under AM0 and AM1.5, and there I saw a little bit degradation, and it retained around 85% of its initial efficiency, mainly because of some damage in the CIGS subset. However, again, there were some artifacts when measuring EQE, and these are related to defects in the CIGS. And so under the right measurement conditions, we could recover the original EQE here. All right. So again, we tried to corroborate this by PL measurements. And here I'm again showing quasi-Fermi level splitting maps calculated as before by exciting with a blue laser just the perovskite. And here we see no change whatsoever in the perovskite subcell. So the quasi-Fermi level splitting stays high, meaning we have a unchanged, identically high quality of the perovskite. And the change in VOC of the tandem is again not because of the perovskite degrading, but because of some small damage in the CIGS subcell. Still though, perovskite CIGS are a lot more radiation hard than perovskite silicon junction. With that, I would like to come to the next big tandem, which is perovskite-perovskite tandem. So now, in contrast to perovskite silicon, perovskite-perovskites are all film-film. So in this case, this is all spin-coated, all solution processed perovskite-perovskite tandem by Charles Apperon. And he's using from a medinium, cesium, DMA, lead iodide, bromide composition for the white gap perovskite, and then a 50-50 lead tin-based composition for the low gap perovskite. Okay, so again, I'm doing an in situ experiment under proton irradiation, this time not using illumination, but instead looking at the radiation-induced current. So what am I doing here is basically I'm shooting with high energy protons, and those will lead to excite electrons and holes in the semiconductor. And because it's in a device, we can extract those and measure a current. I'm trying to show this in this little animation here. So we shoot with protons, excite electrons and holes, which we can measure as a current, and then we can track this current over time to look at the degradation of the device. And I've done this for a bunch of different technologies. So here on the left, I'm now showing the degradation of this radiation-induced current as a function of proton dose for a silicon solar cell, for a silicon carbide diode, but also for a 3-5 triple junction solar cell as it is used in space today. And in all of them, I see the accumulation of defects leading to a degradation. However, when we look at the perovskite-perovskite tandem, it's extraordinarily stable. Most importantly, here, I'm now going up to proton dose of 10 to 13. And before, I've been looking at devices after around 2 times 10 to 12 protons. So I'm a factor of 5 more damaging now. All right. So they look very promising when we look at the radiation-induced current, and I, of course, also characterize them after. And I'm showing now the remaining factor of VOC, the JSC, and the efficiency in maximum power point of that perovskite tandem as a function of proton fluence under AM0. And you can see it degrades to around 94% of its initial efficiency. If you compare this to a standard 3,5 triple junction as it is used right now, this is very stable. So in my experiment, we had a degradation up to around 78%, while literature actually shows that you should have even damage up to 65%. So this is promising. They seem more stable than 3,5 triple junctions on germanium. And just for comparison, here, this proton fluence of 10 to 13 corresponds roughly to 1 year around Jupiter, 10 years in a geostationary orbit, or 100 years in a low Earth orbit. So that could be promising. All right. So now let's try to find out what is degrading in this perovskite tandem. The first thing, of course, is doing EQE, right? And when doing that, we see some damage in the low gap subcell of the perovskite tandem. You can measure also the EQE of the 3,5 triple junction. And in that case, it is mostly the gallium arsenide middle cell which degrades here. All right. So now when only one subcell degrades, this will of course become dependent on the illumination spectrum you have, right? And in the perovskite tandem case, we actually started with a device that was slightly mismatched by the high gap subset under AM0. Under Mars spectrum, for example, the device is very severely current matched by the high gap subcell. But as a result of that, the degradation by the low gap subcell almost vanishes. And I looked into this or found this when looking at the device under AM1.5. So there we almost have no degradation in the perovskite. So I was thinking maybe our friend here on Mars would have been better off using perovskite tandems instead of these gallium arsenide triples. All right. With that, I would like to come to my almost last part. Can we understand the radiation damage in such a perovskite tandem? All right. And what I've been doing here is again PL. So I'm looking at the PL of the wide gap perovskite by exciting it from this side, and the low gap perovskite by exciting it from the other side. And you can do this, of course, after proton irradiation. And when doing that, I see that the low gap degrades in PL, while the high gap actually increases in PL. All right. I was quite puzzled by this result, honestly. So I went for a second beam time, this time with just bare absorbers on quartz glass, well encapsulated. And I again tracked the PL. And this time I found no degradation in the low gap and almost no degradation in the high gap. So the damage we have in the tandem is definitely different to the damage we have in bare absorbers, already telling us, okay, maybe interfaces are important. And we will see this later on as well. So again, as before, I'm now doing a linear fit to the high energy slope of my PL to extract the quasi-Fermi level splitting. And you can do that for a variety of different light intensities, excitation intensities. And then you can plot the quasi-Fermi level splitting of the low gap and the high gap here before and after two different fluences for proton irradiation. So this tells us something about the subcells in the tandem, and these are actually the results from the bare absorbers. So we can now sum the two quasi-Fermi level splittings up to create the sun's quasi-Fermi level splitting graph of the tandem. And again, I observe no damage upon proton irradiation. You can also measure the voltage of the tandem just under reduced light intensity. And if you do that, we get these curves here. And again, there's almost no damage in VOC before and after proton irradiation for these two fluences. All right, this again looks promising. So there's one step we can now do to go further. And this is basically following a publication from Martin Stolterfohr from Potsdam, in which he takes the quasi-Fermi level splitting measured as a function of light intensity. So very similar to what I showed in the foil before. And now you can plot this not as a function of the log of the light intensity, but on a linear scale. So you get this. And now what you can do is just flip the two axes here and subtract light-induced JSC to get a pseudo-light JV curve. And I'm now doing this for the two tandems and the data I showed you in the slide before. And what you get is basically this. So the green curve here is the sun's VOC pseudo JV from sun's VOC, so from the complete tandem. And then here the orange is pseudo JV from sun's quasi-Fermi level splitting of the bare absorbers. And I do this for the 2e times 12 protons per square centimeter and 10 to 13. So now let's look at the remaining factor. So that's what we are interested in. And we can see that the efficiency actually stays the same. And bare absorbers are a lot radiation harder than the overall tandem. Again, telling us that interfaces and recombination layers in the tandem are quite important for the damage. All right. So now let's go on and let's take a step back and look at the radiation hardness of the 3,5 triple junction, right? So there, if you remember and recall the EQE I showed, the gallium arsenide middle cell degraded, okay? So now I looked at this gallium arsenide middle cell a bit more closely, this time using a confocal PL microscope. And here on the left is an image before irradiation. Okay, this is a pentaxidal grown gallium arsenide layer. We would expect a very homogeneous PL. But then upon proton irradiation, we start to see these dark spots here, which appear to be defect clusters. And they're very similar to what is known for the damage from proton irradiation, for example, in polymers or plastic. So there you can actually etch along damage of this ion track. So if you imagine one proton flying through here and damaging the material along the track, and then you can etch this damage to produce these micromembranes. And what we see here in the PL seems to be quite similar. So we see defect clusters probably around the ion track of the protons. All right, so we of course did the same for the perovskite, and now I'm directly looking and jumping to the low gap perovskite because that one was damaged the most. However, we don't see the appearance of any dark spots, but of course, perovskite is not epitaxially grown and polycrystalline material. So it's also hard to see. But overall, we think that damage in 3,5 semiconductors is quite different to damage in perovskites. So in the gallium arsenide subcell, we see these defect clusters because of displacement damage. But in the perovskite, we know from my experiments on just bare absorbers that they are extremely radiation tolerant, but then the tandem degrades a little bit more. And we, at the moment, think that this is because of damage of the recombination layer. So if you imagine the recombination layer is formed by this C60 and then some TCO layer and P.PSS. So if this recombination layer is damaged, you could get all kinds of different PL variations. So you extract less efficient, you have more recombination at that interface. And we think this is causing the damage in the tandem. So with that, I would like to go one more step back. I talked a lot about radiation hardness, but that's not the only extreme in space. There are many more extremes. One, for example, is high vacuum, UV, atomic oxygen, if you're very close to Earth's atmosphere. And I think most of us agree that UV can damage perovskites. And you can see this quite nicely, for example, when you look at the UV degradation of just a bare MAPI perovskite film. And what I'm doing here is I have a mass spectrometer behind a perovskite film in high vacuum. And once you shine light here, you can see the out effusion of methylamine, hydrogen, NH, etc. So the perovskite is decomposing upon the UV. This is a problem for any space application. So we will need a very good encapsulation. Luckily, most substrate materials block harsh radiation, harsh UV light in space. Here are just some examples. But then you could go one step further and use additional down converters to avoid UV light and by that protect the perovskite. So this would be one additional challenge. The other one is extreme temperature cycles. Imagine you're in orbit, you are facing the sun completely, so you're at around 80 degrees, but then in eclipse, in shadow, the temperature will drop rapidly to below 200 Kelvin. So this is something we don't have on Earth, but it can affect perovskites, especially because they undergo phase transitions. Interestingly, there are a couple of studies, for example, by Chen et al. Here, and they showed if you have a temperature cycling of perovskite, you can actually improve the PL and improve the JV curve after that. And they speculate that you heal defects in the material upon undergoing these temperature cycles. So this, again, looks promising. But then you can have very low intensity, low temperature environments. And here are some very nice results from Brown et al. Here from Oklahoma. And they looked at formamidinium, methylammonium, cesium, lead, iodide, bromide perovskites at different temperatures, so using a cryostat. And they tested them under a variety of different illuminations as found on Jupiter, Saturn, or Mars. And their results were super promising. The perovskite worked very well in these low temperature environments, where actually 3,5 semiconductors, again, already would be very poor performing. However, it also depends on the perovskite composition. And the same group has interesting results on tin lead perovskites. And maybe they can correct me after if I'm telling something wrong here, where you can get barrier in the device at low temperatures and certain illumination intensities. All right. So the last thing I would like to mention is there have been a bunch of balloon tests. The first one's already in 2018. There has recently been a successful rocket flight by the Technical University of Munich, showing data of perovskites actually in space. And I think last month, NREL, a bunch of people from NREL were able to launch a couple of perovskites to the ISS. And I assume they're right now testing the devices up there. And I'm very curious to see the results soon. I think we're all interested in that. And with that, I would like to conclude my presentation, basically. So I hope I could convince you that perovskite tandems are an option for space. You certainly don't want to use perovskite silicon tandems because they have a remaining factor of just 1% after proton irradiation, because the silicon here breaks down. Perovskite CIGS are a better choice, though there is some damage in the CIGS subcell and also some damage at the recombination layer. And then I looked at perovskite tandems, which so far showed the best results with a remaining factor of 94%. Both perovskites were extremely radiation hard, and most damage arised from the recombination layer in here. So this is something where we will need to work on just to increase the radiation hardness even more. And with that, I would like to thank the group at Cambridge, where I was with the Theodor Lünen Fellowship, my group at the University of Potsdam right now, and all my collaborators at Helmholtz and NREL around the world. With that, thank you for your attention, and I hope we could have a discussion on other open challenges for space. Thank you.